Okay, let's understand what quantum mechanics will do for us. Quantum mechanics, which was developed independently by Werner Heisenberg and Erwin Schrodinger in 1926, and for this Schrodinger, this mechanics, this theory, this theoretical science, this branch of theoretical physics will enable us to understand and to draw a clear picture of how systems like atoms and molecules, which are very smaller, which are not visible to our naked eyes, and how the electrons are revolving or are present inside atom. It will be well defined or described by this mechanics. It is in advancement with the classical mechanics, which was already there and which is based on the Newton's laws of motion, which describes the falling objects or the movement of the part of planets, like big macroscopic objects, cars and all. But this particular mechanics, quantum mechanics, will be able to describe all those macroscopic objects and the microscopic objects like atoms and molecules and the electrons there are present inside them. So this is an advancement to the classical mechanics because it will be able to describe all the objects which are in motion and the forces that are applied on it and various other changes that those forces produces. So it is an advancement to the classical mechanics. And I heard of this but quantum mechanics is an equation which is known as Schrodinger equation. Just developed where it is a fundamental equation developed by Erwin Schrodinger, for which he won the Nobel Prize of Physics in 1933. The particular equation considers two main things which were developed in 1924. The de Broglie equation, which considers the wave particle duality of all the matters, not only the small matters not just like light. He says that all the matter has a dual behavior. They behave both as a wave and a particle. So he proposed a particular equation which called called wavelength is equal to h Planck's constant by momentum, which is a wave describe which gives the wavelength that will be produced by any object, whether small or big, and this and connecting it to the momentum of the object. So any moving object, whether it's a planet or you or a car or an electron, will have wave, and its wave length can be calculated using this equation. So the way the quantum mechanics, while Erwin Schrödinger describing to describe while proposing the Schrodinger equation, he considered the dual wave particle duality, which was given the de Broglie and Heisenberg's uncertainty principle, which says that it's impossible to calculate precisely both the position and the momentum of objects, especially small objects, microscopic objects like electrons, at the same time. There will be some uncertainty in the position or in the momentum. It is described like uncertainty in the position multiplied by uncertainty in momentum should be equal to more than should be equal to or more than h by 4 pi. This is what mathematical expression of Heisenberg's uncertainty principle. So the Schrodinger's wave equation, it looks like h psi is equal to e psi. E denotes the energy and psi is the wave function of the matter of the subatomic particles, and this is true for all the systems like atoms and molecules whose energy does not change with time. And when we solve this equation, so here the h is known as is a mathematical operator known as Hamiltonian, and this operator, it gives us an idea of constructing. This operator can be constructed from the energy from total energy of the system. The total energy of the system, it will consider the kinetic energy of the electrons and nuclei, or the repulsive potential or attractive potential between the nuclei and the electron. It will consider all those all the total the total energy of the system. And by doing that, we'll be able to solve the equation for the wave function. What will the wave function of that of the system, or and the energy of the system, the energy will be quantized. And during that, we'll be needing numbers that will give this that will give rise, that will supporting the value of the wave function and the total energy of the system. And those numbers will be quantum numbers that will be studied. Although the derivation and the calculation of this, solving this equation for a particular system, maybe hydrogen atom or helium atom or sodium atom or a bigger molecule, that calculation or derivation or solving equation, it requires a knowledge of higher mathematics that we won't be doing right now. We just now to introduce the concept that there's a Schrodinger equation, which is based on the wave particle duality. And solving this equation will give the total energy of the system and the wave function of the system, that the system is having some wave. It considers the de Broglie equations. And while solving this, not only the energy and the wave function can be derived for a particular system, there will be the numbers which will supporting or which will be in agreement with those energy and the wave function, and those numbers will be called quantum numbers.